Right. Welcome back to the next lecture on the DC motor characteristics. So, in this lecture, we try to discuss the basic expressions which we use for the DC motor analysis. And apart from that, so as like we seen in the DC generator, various type of DC generators are there, which are based on the field excitation. Here also we consider same characteristics. So based on the field excitation, so the DC motors are classified into shunt, series and compound machines. And we see these three machines characteristics in terms of torque, current and voltage, torque, speed, etc. So let us see now the basic idea from the machine. Like, so we seen the DC motor, the generalized function of the DC motor look like this. If this is the motor, so the input to the motor is the electrical in nature. So the P in is equal to electrical in nature. This is what the electrical domain, where we deal with the voltage and current. Voltage and current. And once we give the power supply to the machine, so we seen the internal in the last lecture that what is going to be happen is that it develop a torque. This torque we call as electromagnetic torque or the armature torque. So you can represent TA or TEM. So which is so P Z by A. Apart from this, 1 by 2 pi also will be there. This Pz by A is same constant as what we had seen in the EMF equation into the flux into the armature current. So this is what the armature torque. And also we seen in the generator the induced EMF expression is, let me write, Pz by A into the flux will be there. So I had written previously small n. Now I would like to add that with the omega, and I'll put up 1 by 2 pi. This expression also we had seen. So why? Because omega can be written as 2 pi n, where n is equal to, n is in rps, revolutions per second. If I'll use this expression as a 2 pi capital N, so I should divide with 60. So where N is in RPM, revolutions per minute. So instead of small n or capital N, I am using omega. When I use omega, try to observe. So in the torque expression, the constant, and in the induced EMF expression, the constant, both are look like same. So for both of these, so we can consider the constant as k 1 by 2 pi p z by a. So thereby I can write these expressions simply. Ta is equal to k into phi ia, E is equal to, so k into phi omega. Then what is the difference between this induced EMF in comparison with the generator is that here we call this as back EMF. This concept also we discussed in the previous lecture. And once this torque is acting on the armature, then it produces the mechanical power which we call as the rotational power. So that P out is in the mechanical nature. So that the power available at outlet of the machine we call as the torque in the form of torque TSH and angular velocity omega. This we call as the shaft torque which is acting on the machine. And when we go with the schematic diagram of this motor, so as like the generator case, so let me take the armature as like this, and armature has its own resistance Ra, and the induced EMF here in case of motor we represent E, but it is represented as EB, back EMF. Previously if it is generator, we usually represent as EG, generated EMF. And now this armature terminals usually connected across the power supply. What kind of power supply? DC power supply. Let us assume the power supply voltage is V and the current supplied by this is I. See, the power current direction is reversed in comparison with the previous. Previously, it is supplied to the load for generator. So here let me consider the armature current as IA, and if I will consider the field excitation also here, so the field terminals are FF or FFF. So this is RF, and let us say it may be separately excited or self excited, no issue. So as like this. And now we can also look on this is the shaft of the machine. Just let me extend as like this, that may be shaft of the motor. And now try to see that once we give the power supply to this armature, then it develops the armature power pa armature power, which is equal to voltage into current. How much is the voltage developed in this? Eb, back EMF Eb. Current passing through it is Ia. Thereby, this power is helpful for production of the torque in the armature. So, where torque is equal to, or torque into angular velocity is the power. So, we can write the power divided by the angular velocity at which it is rotating. Then after this torque, when we see exactly how much torque is available at the shaft is, that is what the shaft torque. And in comparison with this TA, this TSH is little low. Why? Because here to here there will be certain mechanical system involved, which is bearing and rotational losses or stray losses going to be involved here. So here the amount of the power available is what? The mechanical power. Mechanical power. So how much is the mechanical power? So P mechanical is equal to the available armature power minus let us say friction and windage losses. Friction and windage losses. Friction and windage losses. Windage losses. If I'll subtract these losses from the armature power, I'll get the mechanical power. So once I'll get that mechanical power, or this usually we call as P out, P out. So once we get the P out, we can find the T shaft, which is also rotating at same velocity, angular velocity omega. So that is P out divided by the angular velocity. Always remember, product of torque and angular velocity is what? The power. So this is what the ultimate power, which we call as the net power or net torque. Whereas here gross torque or gross power. The armature power we call as a gross torque or gross power. And now this is the basic idea, more or less look like same as that of the generator. What is the difference is that just simple KVL equation is different. See here. So if the voltage applied across this entire armature is V, can I write V as, so as like this, IA RA armature resistive drop plus left out voltage is what? EB. So previously this might be minus EB, so now this is plus EB. This is one of the important difference. And remaining, just you can see that depends on the machine, this armature current is equal to source current IA. Then remaining expression I already given, PA is equal to EB into IA and torque. So only these torque and power expressions are very important in the generator concept. Now, as we know that this is mainly so works based on the field produced by the field coil. So now let us see how can we put the field power supply. Based on that, let us classify the machines into as like generator. So the machine motor field excitation, let me write as motor field excitation, field excitation, motor field excitation. So if we use the shunt connection, so we call shunt excitation as like the generator. Just let me write that shunt excited DC machine, excited DC motor. Similarly, series excited DC motor, and third one is compound excited DC motor as like the generator, no much difference. So we see one by one. so in terms of its characteristics, so generally here let me say here itself, so motor characteristics is motor characteristics are seen in this way. So just try to observe here what are the various things available. One important thing is this armature torque. How the armature torque vary depends on the armature current. That is what torque current characteristics. So the very important thing, first one is the torque of the armature versus the armature current. As I vary the current, how the torque is going to develop on the motor, so that I will get the mechanical power as the output. So we should understand these characteristics to better interpret the machine operation. So second one is, just see that, so the ultimate output is rotation in terms of the speed. So you can call this as speed in rpm or rotate, what you can say is angular speed omega. In either way you can deal. So ultimate output is the speed. So as we vary the armature current, how this speed is going to change. So we would like to see these characteristics also. That is what speed versus n is the speed versus the armature current. The last one is, see here, so the speed versus torque also we would like to see how the relation exists for this torque and the speed. So that is what the third characteristics. So the speed versus the torque of the machine, that is armature torque. So we see these characteristics for the machine. So now let us take up the shunt excited machine, the one shunt shunt excited shunt excited DC motor. Shunt excited DC motor. And let me take the previous diagram which I already drawn here. So, and let me make this to be as shunt excited machine, shunt excited DC motor. So now let me take here that same diagram. And now how can I make this to be shunt? So if I'll use the voltage across this field winding same as this armature voltage, that is what the shunt excited. So I'll be connecting these across the armature. See this, how I am connecting across the armature, I am connecting. So thereby see this field winding is connected in parallel to the armature. So it is becoming shunt excited. Previous one is separately excited diagram. So now out of this we have to look some important things, that this is the amount of the field current taken from the power supply, and the armature current is IA. Now can I say the source is supplying these two currents, which is IA and IF, which is equal to I. So let me write these equations as like the generator concept which we see. The first thing is that so the source current I is equal to armature current plus field current. And if we see carefully, what is the field current is that IF is equal to voltage across the field winding is, what is the voltage across the field winding? V, which is source voltage. So how much is the field winding resistance? RF. So V by RF is what? The IF, which is the field current. Usually this field current is very small, sometimes negligible. We may consider directly I is equal to IA. Sometimes, so depends on the given question. Now let us see some more things, that here one important conclusion from this is that, see here, observe carefully. So usually the supply voltage is constant. This is what the supply voltage, supply voltage, and field resistance also constant. If the field resistance and the supply voltage is constant, could you see that the IF is approximately constant? If IF is constant, try to observe the flux produced inside the stator windings, stator coils, is also constant. Is also constant. That means if it is a shunt machine, it is practically, we can assume that the field flux is practically constant. So for shunt machine, shunt DC motor, DC motor. So phi phi is assumed to be constant. Phi is assumed to be constant. But in reality, as load varies, means if I'll add any load here, mechanical load here, if I'll add any mechanical load, then if load is increased, slight amount of the decrease in flux may take place, but that is negligible. That you have to keep in mind. That you have to keep in mind. If you want, let me write. Let me write. But uh, but like as load increases or load increases, as load increases, there may be there may be small small reduction in reduction in flux flux phi, field flux phi. This is what in practically, but it is a good approximation to consider as a constant for most of the things. Why? Because we may not go with almost every time beyond the full rated value. So this is in practical, but one can assume so approximately flux as a constant for the DC machine. Okay. Right. So now if we consider flux as a constant for this DC machine, can you see this torque is proportional to phi into Ia? That what we have derived, just see this, torque is equal to phi into Ia. So here see that torque, this entire thing is constant. So torque is proportional to phi into Ia. If field is kept constant, means constant excitation. So here phi is constant. So thereby, so the torque is proportional to simply current. This is one of the important expression. And of course, this is the armature torque, TA, armature torque TA, armature torque TA. This is one expression, and let us see one more also, that is what the speed. So we know from the generator concept, E is proportional to phi into N, phi into N. So can I say this N, or you can say this phi into capital N, both are same. So if this is the case, here it is a motor, so let me add EB, EB is proportional to phi into N. So now can I say the speed, which is important for us, the speed is proportional to EB by phi. But if phi is constant, so if phi is constant, what can we say? If phi is constant, for a shunt machine, we said that in all practical applications, this may be assumed to be constant. That may be a good approximation for the analysis point of view. So if this is constant, now can we say that N is proportional to EB? N is proportional to EB. So this also one more important equation, so which we need to understand. So now let us see here, some of these characteristics. So based on these expressions, so the first one is assume like this. So the torque on the y-axis and the corresponding armature current on the x-axis. Now just see this, this is a direct proportional relationship. What might be the corresponding the characteristics, how does it look like? It look like a straight line. It is a proportional linear relationship. So the characteristics look like this. As current increases, torque also increases. As current increases, torque increases. So this is what we call as torque versus current characteristics. Just based on these expressions, we try to interpret these characteristics. No much logic behind this. So next is, let us take the next one as the speed versus current. Speed versus current. So now let me take this one more thing. This is again current, but now I would like to take the speed. So here we should otherwise let me say in this way. So can I write this one as eb is equal to v minus ia ra, v minus ia ra. Clear? So what is eb? Eb is proportional to speed. Now can I say the speed n is proportional to v minus ia ra from these two expressions? Why? Because eb is indirectly equal to n, which is direct proportional. So I can say speed is proportional to v minus ia ra. Now try to observe first what is ia ra expression in practically. In practically, we seen this also previously. So in practically, see here, if ia is small, so ia ra drop is also small. So this is what the ia ra characteristics. As ia increases, ia into ra, current voltage drop also increases. But as because ra is very small, this drop will be usually very small. So consider for ideal case, for ideal case, this is for practical case. For practical case, practically ra will be there, but for ideal winding, armature winding, this ra may be 0. If ra is 0, try to see that what will be the speed. Speed is just you can say the, like you can say it is almost constant. Why? Because in this way, let me write this as v means supply voltage, it is equal to supply voltage. So what is the nature of the supply voltage? Supply voltage is not a variable voltage, it is a constant. So the speed almost constant, no change in the speed. In which case? In ideal case. So let me put those characteristics, whether current is 1 ampere, 2 ampere or 100 amperes. So let us say the no load speed is this much, and that will continue, that will continue as like this. This is what ideal characteristics. The speed is constant, so that may be equal to no load speed. What we call as no load speed. This we call as no load, no load speed. So, but practically, how does it look like? Practically, we need to subtract, means that speed reduction, instead of just in terms of subtraction, just think of just in this way. If current increases, IRA drop increases, then V minus IRA will try to reduce this entire term going to reduce as IA increases. Why? Because just see here in this way that IARA drop is rising, varying. So as IARA increases, V minus IARA is decreasing. That means now the speed going to reduce a little bit, very small, not too much. So very small. This is what the practical thing. Practically, the machine, the speed is n, that is what the speed, versus the current, which is the armature current. So now try to observe for a DC shunt machine, the speed is almost constant. So almost constant. So we can use these kind of DC shunt machine in constant speed applications. So it is very much suitable for constant speed application. So based on these speed versus current characteristics, we can assess that this machine is suitable for constant speed applications. So it doesn't matter what kind of load you are connecting, whether it is 1, 2, 3 or 100 amperes. So for any current, it try to give almost constant speed. That is what the advantage of the DC shunt machine. And one more thing, let us see here that we know usually the machine power is constant. So can I say the armature power, the armature torque into its corresponding angular velocity is what the power? Which power? Armature power. How much is this? EB into IA. EB into IA. So in reality, this will be almost constant. The amount of the power developed in the armature for a shunt machine is constant. We had seen EB is equal to V minus IARA. So IARA drop is negligible. Just see here. Just see here. So EB is equal to V minus IARA. As because armature resistance is small, this is negligibly in comparison to the applied voltage. So this goes 0, then it is almost V, which is almost constant. So like that, so this entire thing's going to be almost assumed the constant power is developed across the armature. So if the armature power is constant, we can think of, see here, what will be the speed versus torque nature. Speed versus torque nature. And we know that this omega can be written as 2 pi n by 60. So can I write this one? Ta into 2 pi n by 60 is equal to constant. Then I can write from this as simply the speed is proportional to 1 by Ta. 1 by Ta. See here, if I will consider this speed term, so this 1 by Ta will come in this way, and this is what the speed versus torque. Now you can see that, so how it look like. The characteristics of this will be, so if I'll consider this as a torque Ta, this as speed N, so it is inversely proportional. That means as the torque increases, speed decreases from certain value like this. So see, as current in torque increases, so the speed is falling down. The speed is falling down. So this is what the speed versus, let us say this is the no load speed, initial speed. So it is reducing. So this is what we call as speed versus torque characteristics. So all these characteristics are just visualized based on these expressions only. The torque and its corresponding current are just basic schematic diagram of this DC machine. So these are the three important characteristics of a DC machine, DC shunt motor. This is the third one. Okay. So now let us see the series excited DC motor. Series excited DC motor. So I will consider the same diagram that what I had seen previously. So what change I will do is that, just let me add the heading that DC or series motor, series excited DC motor, series excited DC motor. So let me quickly just you know it. So what I'll do is that instead of connecting this field winding in parallel to this armature, now I'll create some space here, and I'll try to connect this armature, field winding over there. So this entire field winding, so let me take over there and let me make a little smaller. So right, so let me bring here and connect over here. Now see that, so just let me remove this field current also. I'll tell you the direction should be in the direction of the current. This is what the field current IF now, and it is connected in series with the armature. Check it. So now just based on this schematic diagram, we have to look for some of the things as like this. So try to see what will be the currents. IA is equal to IF. These are the generalized thing. Quickly observe. And if IA is equal to IF, so can I say the flux is proportional to the applied field current? If flux is proportional to the field current, as because IF is equal to IA, can I say the field flux is proportional to the armature current? This is one conclusion directly. Next is that, so we had seen that induced EMF in the armature, EB, the next point is that induced EMF in the armature is proportional to flux into the speed, flux into the speed. So this proportionality relationship we can write in this way. EB is proportional to, see phi is proportional to Ia means I can replace phi with Ia. So I can write this as Ia into omega. This is the second important conclusion which we can utilize for drawing the characteristics. The third conclusion here is the torque. So we know torque is proportional to flux into armature current. But for series machine, what is the flux? Flux is proportional to armature current. So can I say this TA is proportional to Ia into Ia, which gives it is proportional to Ia square. See, I am using only one simple expression which is torque and another simple expression is induced EMF. Based on these two and based on the schematic view of the machine, so I am trying to interpret some results. So these are simple, but you have to observe very carefully. And now just see this as like in the previous case. The power of the armature, the power developed in the armature is constant. That is what PA is constant. So a constant power is developed across the armature. So that is PA is equal to constant. Can I say this as EB into IA is what the constant? So what is EB? EB is proportional to Ia into omega. So can I write this as Ia into omega into Ia is constant? So now see here, the Ia square is proportional to 1 by omega. This is also one of the important relationship. Now, once Ia square is proportional to 1 by omega, the conclusion point here is that the torque developed across the armature is proportional to Ia square, where Ia square is proportional to reciprocal of the angular velocity. So, can we say from this TA is proportional to 1 by omega. So, we use all these boxed information to draw the characteristics. Now let us see what will be its corresponding thing. So let me say the first one. What is that? So the torque versus the armature current as like the DC shunt machine. So now immediately keep that expression over here. What is the torque versus this current? Torque is proportional to Ia square. That what we had seen. So this look like a quadratic equation. So we can say this TA look like parabola. So this is Ia. So as current increases, the torque increases, but it is not linear. Look like this curve nature parabola. So this is what the TA versus Ia. TA versus, if it is just T is proportional to Ia, it would have been a straight line. But this is proportional to Ia square. So if I'll consider, so 2 amperes, then that corresponding torque will be square root of TA. That means for large variation of the current, so small variation in the torque, like that you can interpret. Okay. So the second one is that, so the speed versus Ia, the speed versus Ia, these three characteristics we usually describe. Same x-axis is Ia and y-axis is the speed n. You can consider omega also, no issue. So speed is indirectly omega. Now see what is that? Let me write here the speed versus Ia. What is its corresponding relationship? Speed versus Ia. So we seen this that can I say in this way? So Ia square is proportional to 1 by omega. That means omega is proportional to 1 by Ia square. So as like the torque expression here also same but reciprocal. So if there is any increase in current, decrease in speed will take place. So it is quite opposite in this way. So this is what the omega or the speed versus ia ia curve ia curve. Just interpret these expression. See, if ia is 0, speed is infinite. If ia is infinite, speed is 0. So it matches these things. If ia goes infinite, speed comes to 0. If ia is 0, then speed goes infinite. 1 by 0 is infinite. Like that you can interpret. Similarly, for the other characteristics, so that is what the torque versus the speed, which we already seen that. So torque is proportional to 1 by omega. See here, somewhere torque is proportional to 1 by omega. See here in this expression, torque is proportional to 1 by omega. So now you can say, depends on your requirement, omega is proportional to 1 by Ta. See, it is inversely proportional relationship. So if torque is 0, speed is infinite. So it look like almost torque versus this speed versus current nature. So let me say here, this also look like same. That does not rise, just it will keep on falls and so on like this. So this is what the speed versus n versus torque. So these are the three characteristics for a DC series machine. So here one important conclusion when we talk about the DC series motor is that, just make a note, and this is very important for competitive exam. Try to see that in any case, by any means, like, so due to some problem or any kind of thing, if the armature current is 0, if the armature current is 0, what are the consequences we would like to see? That means armature current when it is 0, when the machine runs, when machine runs under no load, runs under no load. If the machine is not loaded, usually the current drawn from the power supply will be 0. That is what the armature current is equal to 0. So if it runs under no load, that is one thing. Or suddenly once machine is running, just see here, if armature conductor got broken, some open circuit fault taken place, that also lead to current to be 0. So like that, it may be under no load condition, or if any fault, open circuit fault, open circuit fault. If any of this situation occur, then armature current will be 0. If the armature current is 0, we know that, see, Ia is equal to If is also 0. If If is 0, as a consequence, field flux is 0. If field flux is 0, try to observe what is the speed. Speed is proportional to 1 by Ia. Just see this expression. Speed is proportional to, somewhere I had written, where is that? Speed is proportional to, see here, 1 by Is square for series machine, for series machine. So this one, 1 by Is square. So let me write Is square here also. Yeah. So here also 1 by Is square. So in that case, if the current is 0, the speed will be infinite. Means the machine will attain dangerously high speed, thereby machine will get damaged. So it is advised that in a series machine, never start that series machine of or DC series machine on no load. So make a note of this. So the series DC motor, DC motor is not allowed, not allowed to start to start under under no load condition, under no load condition. That means what we need to do to start the DC motor, series motor, is that initially you apply the load first. Before starting it, first connect the load. Once load is connected, then you try to start the machine, so that the speed does not attain infinitely large, so machine does not get broken. That is one thing. Other thing is that once machine is running, you are not allowed to disconnect the load also. So load must be there on the machine always, not only during starting. So the, just let me write instead of this way. So the series DC motor is not allowed to run under no load condition. Instead of start, just let me say to run under no load condition, to run under no load condition. So never run the DC motor under no load condition. This is one of the very very important point. So in many competitive exam, people will touch this point, that so they'll give many ways like, but this is the ultimate summary, that we should not start the DC series motor under no load condition. And let me quickly complete this compound motor also, and which is simple thing. So compound DC motor, and for which let me take the same diagram here. So this diagram, let us say, so once you have the awareness on the DC machines, that is generator, it is easy to interpret what kind of shunt series compound. So here this field winding I will call as series field winding. We know that here two field windings are there, RSE, and this current also I will consider as ISE. ISE, series field winding current. And let me connect one shunt field winding over here. So that field winding is having a resistance of RSH. Now let us connect this terminal over here across the power supply. This may be long shunt machine. So this terminal over here. So now the current drawn by this is what, ISH, and this is ISE. So the total current, let me put instead of here over other place, that is what the current supplied by this is what, the I from the source. Now for a compound machine, just let me quickly write down these things. So I is equal to ISE plus ISH for this corresponding thing, and IA is equal to ISE. This is long shunt DC motor, and remaining expressions same. So as like this, so you can also say ISH is equal to applied voltage divided by RSH. Just from the circuit analysis you can make these expressions clear. So next, apart from this, see these power expression and torque expressions remain same, no change in that. So now try to observe clearly here. What happens here is that in this way, let us say like, just let me write here. What I want to say here is that initially, 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 speed is 0 for the machine. Speed is 0. Before starting the machine, the machine is at rest. Speed is 0. If speed is 0, if speed is 0, so no current, no current flowing, flowing in series winding. Why? Because machine is not rotating. If machine rotates, there will be a mechanical load, thereby it is demanding some amount of the armature current. So no current flowing in series winding, series winding, that is what IA is equal to ISE is equal to 0. So if ISE is 0, can I say the field flux produced by the series field winding is 0? Then in that case, just the conclusion point here is that the machine, the machine, the machine initially starts as starts as shunt excited machine. Shunt machine excited machine. See here, so just we trying to interpret. So before, just machine is set up, but still the machine is not started, but we connected this entire connections. What is the thing? As machine is not yet started, so initially the current through this armature is zero. If armature is zero, field flux produced by this field coil is zero, but this power supply is connected across RSH, so ISH will exist. So can we say the machine initially starting as a shunt excited machine, right? So next point is that, right, so it is shunt excited, slowly it is building up the induced EMF, back EMF, that is producing the torque, and machine is going to start. Thereby IA is going to rise slowly. So I'll say in this way. So under no load condition, under no load condition, under no load condition, the IA is small, IA is small, the armature current is small. So thereby the field flux produced by this series is also small. So machine acts as predominantly shunt excited, shunt excited. See, these are the like important initially when speed is zero. So under no load condition, what are the situation for this machine, so that we are trying to interpret. So next let us take under load. So under load, under load condition. So what happens is that phi SE reaches to its rated value, reaches to its rated value. Now, finally, finally, the flux in the core, finally, the flux in the core, in the core of the machine, the total flux will be like this phi SH, which already produced, so plus phi SE, series field flux. But this may not be always plus, depends on the field connection. If I'll reverse this terminal, let us say this is the F terminal, this is F terminal. If I'll reverse these terminals, then field flux may be negative, the net flux may decrease. So it or the net flux may be phi SH minus phi SE also. So when we use this plus, when we get this minus, is that if it is of cumulative compound, cumulative compound DC motor, cumulative compound, then field flux will be additive in nature. If it is of differential compound, the field flux will be difference between the shunt and series field, differential compound. There are two kind of things based on the field series field connection. Series field flux may aid the shunt field flux, then it is cumulative. If series field flux opposes the shunt field, it is differential compound. So this is one of the important characteristics, just you need to so aware of these things, that phi SH and phi SE, how does it look like. And just let me show one important characteristics of this and let me conclude. So here just I want to compare different kind of machines. So that is the important characteristics is the speed versus current. So we seen that for a shunt machine, so practically just constant as like this, sorry. So it is just like constant, so almost constant. This is for what? Shunt machine. And for series machine we had seen, so how does it look like? It will be decreasing like this. Let us say at rated, these are the things, these are the rated speed. At rated speed all might be reaching to the same value. So this is what the series machine. Why? Because inversely proportional, n is proportional to 1 by is square, some kind of thing. So now let us put these cumulative and differential compound machine speed versus current character. If it is cumulative, it is above the shunt characteristics. It will be above the shunt characteristics like this. So this green color is what? Cumulative compound machine. Cumulative compound DC machine. If it is differential, the flux will be low, so it will be under this shunt excited machine. So this you need to observe. And it does not increase, it does not decrease, it try to increase a little bit. This is what the differential compound machine. Just try to remember these things. These will be asked in mostly objective questions. So how the cumulative compound characteristics look like, how the differential compound characteristics look like. So this is one of the important characteristics. So just you can think of even the torque versus armature current also. Just let me put up that if you want, or just you can refer anything. So just let me finally put the torque versus armature current for these cumulative and differential. And if it is a shunt, so we seen it is almost constant. So if it is a series, so it try to increase in this way, like parabolic kind of thing. This is what the rated speed. This is what the rated speed at rated. So let us say all are equal rated. So this green color is the, sorry, blue color is the series. This black color is the shunt machine. Now the characteristics, if it is of differential compound, so if it is of, let me choose same color for differential, red color. So here let me choose red color. So it is quite opposite. For differential it is upward, for cumulative it is downward, but it is above the series characteristics. So as like this. So just this green color is what? So let us say cumulative compound, whereas this red color one is the differential compound. Just observe that where these characteristics are lying. Is it above the shunt or below the shunt, and below the series or above the series? So this way just try to interpret these compound machine characteristics. Okay, thank you.